Okay. I don't know where everybody is. Maybe because it's getting warm? I don't know. Kind of warm. Any questions before I get started? Materials continue to roll in that people have ordered. And as you guys are likely aware, I've just been gathering them and I have them in a cabinet in the lab. And so at the beginning of each lab section, I'm just getting everything out. If you can't find it, let me know, but dig through there and see if the stuff that you ordered is included. I kept all the packing slips in all the DigiKey boxes because there's a bunch of stuff in those boxes. So you can just look at the packaging slip and see if your thing is in there. I think almost everything from DigiKey has arrived. There's one more package today that I haven't picked up yet that I think is maybe the last of that stuff. Adafruit's been just a little bit slower, but I think that stuff's almost all here as well. Any questions or concerns from anyone about, I don't know, materials things or anything else? Yes?
I just ordered my stuff yesterday. What's the ETA on that?
Who knows? I don't know. I would plan not to receive it. Okay. So make sure that you're continuing to, that your project does not critically depend on whatever you've ordered, given that we're already so far in. Yeah. All right, anything else? I wanted to take just a few minutes at the beginning of lecture to talk through final project demo and deliverable logistics, because I've been getting a few questions about that. So it seems like a good idea just to talk about it. We run our final project demos and deliverables in a very similar way to Professor Scavira in 5725 in the event that anybody's taken that class. So just to summarize, you have all now been given access to a final demo time slot sign-up sheet. You'll sign up for that. In that time slot, what we will do is go through you will demonstrate what you've built. And for examples of what these demonstrations look like, I have previous year's student demos linked up on this YouTube playlist. You may, if you want to get a sense of sort of how these things kind of go, you could watch a few of these and just get a sense of it. Generally speaking, it's largely informal. I'm just going to invite you to tell me about what you've built and explain a bit about how it works. If you go through this, you will notice that the amount of time that these demos take vary.
Skip the line and get right to your destination.
There's a lot of variability in the time that these demos take. Some are as short as, I don't know, 3 minutes or so. And if you scroll down, you'll find others that are considerably longer, 15 minutes, or some of these are as many as 20 minutes. The length of these demos basically is entirely up to the students. The way that I think about these demos is it's your opportunity to present your work in whatever way you would like. I'm going to ask you some leading questions to sort of, invite you to talk about the interesting aspects of it. But it's your work, and I would like for you to talk about it as much as you would like. It is a good idea, I'll just mention, before we start these conversations demos, think through what you would like to say. You don't necessarily have to write out a script that you memorize, but it's good to have your thoughts organized so that when we start talking, you have a clear sense of here's what I'm going to explain. And if you watch any of these, what you'll notice is I basically start every demo with an invitation to just tell me about what you've built and how it works. And then you can tell me all about it. And I'll ask you some questions, about how it works. My goal in these demos is not to play gotcha with you guys. I'm trying to help you explain what you've done. And so you don't have to worry about me trying to poke holes in any of your explanations or anything. I'll just help you add clarity, is really the idea. I'll mention also that most students elect to do their final demonstrations in the way that I've documented here. There are some student groups in the past who have preferred to make their own final demo video for whatever reason. Sometimes their projects only work in some strange environment. It's meant for outdoors in the woods or something like that. That's a little bit hard for us to access, but they want to present it in the environment in which it was meant to be presented. That's perfectly fine as well. We will still have a conversation in which we talk about what you've done, but if you would like to provide me with a video to include in this list, I'm perfectly okay with that. So really, it's however you would like to present your work. There was something else I wanted to mention about this. audio as well. Some projects, there's a lot of projects that are very audio focused, and some of these audio projects are doing things like spatialized audio, which if we're just getting the audio from like my phone microphone, you don't pick up. So some students in the past as well have not sent me videos, but instead sent me audio files and asked that I overlay those on top of the demo videos. And I am perfectly happy to do that. There's an example of that in here. Oh, there was a project a couple years ago called Spatial Audio Murder Mystery. And if you find that would be an example of that. That particular group, I'll just mention incidentally, they use spatialized audio to create not a video game, but an audio game. And so you'd put on headphones and you could hear conversations going on. And when you turned your head, it would bring that audio to the center of your attention. You could hear it. And by eavesdropping on various conversations as you moved through an imaginary building, you had to try to figure out a mystery by listening. It was very cool. And so for both those reasons, look up that project. It was a cool project. Any questions about the demos? Anything I forgot to mention, Bruce? Yes, upper limit of 20 minutes for the demo time. If you want more time than that, talk to me. Okay, we can figure out how to do it. But if you're scoping this, that's probably about a reasonable upper limit. Any other questions about this or how these work? And let me just clarify again. You're under no obligation to have your demo made public. If you would like to have it made public, I'm happy to do that. If you prefer to keep it quiet, that's perfectly okay. It's totally up to you. You just specify that in your final web page, which is the next thing I'm going to talk about, unless there's any further questions about the demos. Okay, so we'll demo your final project, and then a week-ish later, I'll post an assignment on Canvas with an actual due date, but everyone will have at least 1 week after their final demo to compose the final deliverable for the class, which, as I've mentioned before, is a web page. You can find all of the previous student web pages for the RP2040 at least linked up here. You might consider just clicking through a few of these. What you will observe as you click through these is that they vary considerably in way of aesthetics. Some students really like, I don't know, JavaScript and HTML stuff, and they make kind of flashy web pages, and that's perfectly okay. Others elect to make slightly more bare bones web pages. That's also perfectly okay. Your grade bears no relationship to the aesthetics of your web page. What does matter, of course, is the content of the web page. And so what you should observe as you click through all of these is that the sections are largely the same. And the place to look for information about what to include in this web page is on the final project assignment link here. There's a section on the final report. There's also a section on the final demonstration that you can read about. But there's a section here on the final report that asks for you to include the following information. And a lot of this stuff is very similar to the stuff that you would have included in a lab report, just sort of expanded because you've had more time to do this. But there's some additional stuff for the final web page, and so please just make sure you read this carefully. So you'll be asked to include a project introduction, a high-level design overview, program and hardware design, your results. Keep in mind, it worked is not a result. Results are generally quantifiable. So this is a section to actually think very carefully about. How do we communicate the results for what we've built? For some projects, that tends to be rather obvious. The project just sort of lends itself to a clear explanation of what the results of that project was or were. For others, it really takes some thought about how you're going to communicate how well you built actually works. How do you measure its performance and report it? So please give some thought to this section. There's a conclusion section, of course. Let me see here. What I wanted to direct your attention to, and I mentioned this last time, but only briefly, so let me just be very clear. One of the sections that you are asked to add is permissions, in which you opt in, if you want to having your project included on that list of student web pages, or having your demo video included on the student or on the course YouTube channel. Why might you want or not want to do this? In the event that you have ambitions to patent your final project, and that's happened sometimes in this class, I would advise against posting it publicly. The reason being that if you make a public, this counts as a public IP disclosure, posting this web page. Once you make a public IP disclosure, it starts a clock that I think lasts 1 year. And within that 1 year of your public IP disclosure, you have to have filed a patent. Bruce? 1 year in the US and 0 everywhere else. So if you are contemplating filing a patent on what you're doing, talk to me about it and we'll make sure that we don't do anything that would inhibit those ambitions. But that would be an example of a reason why you might not want to publicly disclose this stuff. Frankly, or just if you're a person who wants to keep stuff private, that's perfectly okay too. You don't have to have a good reason. You don't have to have any reason, right? Just if you want to, that's great. If not, that's great. I just wanted to provide that as one, perhaps one reason why you might elect not to do this publicly. By the way, you have to include this. You're going to be docked 5 points just immediately if we don't have your permissions. Yeah. So why might you want to put it up? Well, keep in mind that when you turn in this final project web page, you will not be sending me a link. You are perfectly welcome to host your web page on your own websites. It's your project, do whatever you want with it. But in addition to that, you're asked to give me the HTML associated with the web page so that I can host it on a Cornell site. Maybe you would kind of like to have your project hosted on a Cornell site. I don't know, you can go into a job interview and they can say, oh, tell me about a project that you've done. And you can say, well, go to cornell.edu and I'll guide you through the links to get to my project. Okay? I don't know, it lends it a certain credibility, which sometimes is nice. And by the way, it's a credibility that it deserves. These are all great projects, and we're very, very proud to host these projects on a Cornell server. We'd be delighted to do so. And if that ends up helping you in the future by just giving a bit of credibility to your project, then that's great. I feel great about that. Bruce? It does. Every time that I get an email from a former student saying, hey, could you provide a letter of recommendation for this or that or the other thing, the way that I refresh my memory about that student's performance is often by way of these project links. You might also, incidentally, I just like making my stuff public because it makes me feel good that perhaps some other folks will find it useful or use it as a starting point for their work. So it's sort of in the spirit of open sourcing things, which I like doing. I think it's good to open source stuff. Okay, any questions about any of that stuff? There exist, I'll just mention, a bunch of online tools and services that will sort of make websites for you that you are very welcome to use. I've had students in the past also go through the previous student web pages and find one that they kind of like. Just choose one at random. I don't know. Maybe you quite like the aesthetics of this previous project. You're perfectly welcome to just download the HTML of this project and modify it to replace the content here with your own content. That's perfectly okay. You can, my favorite way of making web pages, you may have noticed that all of the web pages for this class and all of my own web pages kind of have this aesthetic to them. That's because I generate all of these in Jupyter Notebooks. Jupyter Notebook has a download as HTML feature that works fabulously. And so if you're looking for an easy way to make, I like the Jupyter Notebook aesthetic. It's kind of textbook-like. You could use that. I think Google Docs even has a download as HTML feature, right? So it does not have to be fancy. It just needs to be some HTML that I can host. Be careful with Microsoft Word. And before you turn it in, please, please, please test thoroughly that it actually works. How do you test this? Download the raw HTML, and if you double-click your main HTML file that links relatively to any other HTML files that may be included in that repository, make sure all the relative linking works on your machine, zip it up, send it to your friend who has a different computer with a different operating system and go through the same exercise, make sure everything still works, then send it to us. And there are, I'll just mention, some pretty specific instructions with regard to how you will submit this. I'll just summarize that I'm going to make a box repository. It's a nice, secure place for us to trade files that I'll give you access to. You will be asked to turn in your final web pages as zipped directories. And there are some rules with regard to what you should name that zipped up directory and what you should name the main index.html file in your own project. That just makes my life a whole lot easier when I'm getting all this stuff up on the website. Otherwise, it becomes very time-consuming to try to figure out how all these local directories work. So please just make sure you follow these procedures. Some things that always get students every year. HTML case sensitivity often matters. So if you are hosting an image, for instance, or loading up an image, all caps PNG and lowercase PNG, they might not be treated differently on your machine, but you send it to your friend's machine and the image doesn't show up. Right? So please just be careful of all of these things. Something else I wanted to mention. Oh, the other thing I wanted to mention. Please try to keep the total size of these files reasonably small. You don't need outrageously massive photos here. If your photos are of some tremendous resolution, please size them down so they're, good enough. They don't have to be 4K. And if you want for your web page to include video, please do me the favor of put that video on YouTube and then embed the video in your HTML rather than sending me the big video file. If you have not done this before, YouTube makes it hilariously easy to embed in HTML. You go to any YouTube video, you click the share button, there's an embed button, a bunch of HTML comes up, you copy paste that into your HTML file, and then when you double click it and it opens in the browser, there's the video ready to go. That incidentally that's how every video works on our course pages. It works for playlists as well. So this is an embedded playlist. Okay. Any questions about logistics? Any questions about the final web page? Any questions whatsoever? Okay, that being the case, then I'm going to continue on with some topics of relevance for final projects. The stuff that I would like to talk through includes, there's a number of groups using stepper motors. So I want to talk a bit about stepper motors, how their internal mechanism and how we control them. And then I want to start a conversation on Wi-Fi communication with the Pico W. We'll start with a conversation about how we connect to a network. And then I want to have a conversation about exchanging information through that network by way of UDP and then, time permitting, TCP as well. But we'll start with UDP. So let me start by talking about stepper motors. You may recall from our conversation about DC motors that the internal mechanism of a DC motor involves a stator field, often set up by permanent magnets. Inside, there's an armature of wire that we're sending current through. And then there's a torque exerted on a current-carrying loop in a magnetic field, right? That tries to align itself with a magnetic field. So we send current through here, it tilts up, and then this commutator device, at precisely the right moment, switches the direction of current through this armature so that it then continues to get torqued down through the rest of its rotation. Right? And that is the mechanism underlying a brushed DC motor that creates these very, very high-speed rotations. The underlying mechanism in a stepper motor is very different. So let me just mention, what are these great for? These can really spin. So if you need a really high-speed motor, you're probably in the realm of DC motors. For instance, for like lifting drones or something like that, where you need to spin really fast. Now, many of the drones motors are brushless DC motors as opposed to brushed DC motors, but the underlying mechanism is pretty similar. A stepper motor is very different. A stepper motor is great for applications where you need very high torque at very low speed. So examples might include 3D printers for moving the little end effector around. Those are very often stepper motors in there. Examples might include those little steppers that some of you have seen lying around lab or have started getting to work in lab. Those, I believe, they sell a lot of those for HVAC systems for moving the flanges on, air conditioning units or something. Those things don't have to toggle super quickly, but it takes quite a bit of torque to move that up. Yeah.
Is it typical to see stepper motors in manufacturing equipment?
Yeah, sure. Yep. Yeah, any application where you don't care about moving super fast, but you really need a lot of torque. And it's a surprising amount of torque. If any of you have gotten one of those little stepper motors that we have in lab spinning and grabbed the shaft, I can't stop it with my fingers. It's really a lot of torque. That torque comes from a very different internal mechanism than the DC motors. This is a highly, basically as simplified as I could manage picture of the internal mechanism in a stepper. Inside of that stepper, attached to the shaft, there exists a permanent magnet, represented here by the little north-south bar. And then surrounding that magnet, there exist electromagnets that we can turn on and off by way of a loop of wire that is coiled around the electromagnet. You send current through this wire, it generates a magnetic field which electrifies this electromagnet, right? So we can depending on the direction that we send current through this loop, for instance, we can either make that end of this electromagnetic north or that end north. We get to pick based on the direction of the current. There's at least 2 of these, right? So 2 wires coming out here, 2 wires coming out here. Those of you that have been messing around with the stepper motors in lab will have noticed that there are 4 control lines coming out of those stepper motors. Those control lines connect directly to these loops of wire going around the internal electromagnet. By the way, you buy a stepper motor, and for whatever reason you can't find the data sheet, how would you figure out the pinout for this thing in the lab? A connectivity test. Yeah. So what you will find is if you use a multimeter and put it in the connectivity beep test mode, you can figure out which of the pinouts are connected to the same electromagnet and which ones are connected to different electromagnets, because continuity tests this loop of wire and it's going to show no resistance effectively. So how do we actually control this? Well, you can imagine perhaps that in this orientation, we would be sending current through that electromagnet such that the top of this vertically oriented electromagnetic would be south, the bottom would be north, which makes the interior permanent magnet have a single stable configuration where north gets attracted to south and south gets attracted to north. And you can imagine that if we wanted to rotate this, one way we could do it is turn off this electromagnet, turn on this electromagnet, and make that south and that north, and the thing would click by 90 degrees and rotate so that it's now in a new stable orientation based on the magnetization of our internal electromagnets. Now, I mentioned that this is a simplified picture. The way that this actually looks, if you look inside, is this internal electromagnet kind of looks like a big gear, where there's little teeth all over it, all around. And likewise, these electromagnets have similarly shaped gear appendages coming off of them. The consequence being that the steps that you can take with a stepper motor, you don't step it by 90 degrees, you step it by a much smaller amount. A degree, 1/2 of a degree or so, so you can click, 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 click it around. Every time you click it, what you're doing is changing the magnetization of these internal electromagnets to create a new stable configuration that's right next to the old stable configuration. But then once you've got it in a stable configuration, its holding torque is awesome. You may have experienced this too. If you have one of these stepper motors powered up and you're not stepping it, but you grab the shaft and try to twist it, it's really hard. It's really, really hard. You get a whole lot of holding torque. These two, just like with the, we are adjusting the current through inductors quickly here. Every time that you're doing that, you're going to get large dIdt terms. And so that implies the necessity for snubber diodes. Correctly implies that. It is often the case that I'll just mention that when you're working with one of these stepper motors, often there's a stepper motor driver, and usually it's the case that your microcontroller is sending commands to the driver. The driver is then subsequently sending the currents through these stepper motors. The reason for that is it's often the case that we're running the stepper motors at higher power than we're running the microcontroller. You might be running these at, I don't know, more volts, more current, etc. And it's that control board that mediates between the lower power microcontroller side of things and the higher power stepper motor side of things. It's often the case that those drivers also provide you some of the protection from the noise that these things are generating. And so that's why, for instance, when folks in the lab were prototyping with our little stepper motors, we didn't have the same long conversation then with those stepper motors about isolation as we did with the DC motors, because we were using this mediating control board. Those control boards I'll just mention come in a bunch of different flavors. The ones that we have, there are pins that represent each of these control input pins, and we step the motor by sending pulse sequences, which I can talk more about in just a moment, but we send pulse sequences into these things that actuate the motor around and around and around and around. You can get other ones that you just send a single pulse train in, and there's more logic on board the control board that then translates that into the step sequence commands. Any questions about that? So they work very differently from a DC motor, and we interact with them extremely differently from a DC motor. A DC motor, we're basically applying voltage and off it goes. These, every time you want for it to move, you change the high-low settings of your various inputs. There exist, by the way, 4 input steppers and 6 input steppers. There may even be more varieties, but you can imagine it represents sort of the number of electromagnets in here times 2. Let's just see, actually. I'll bet there's a better picture. Yeah, here, this kind of is a slightly less simplified version of what's going on. You can see that the internal magnet here has this kind of geary shape to it, and then the electromagnets likewise have that kind of ability to mesh so that we can take higher steps of smaller sizes, right, related to the size of those gears, effectively. So we've talked about stepper motors, we talked about DC motors. Of course, there are other mechanisms of actuation that are perhaps worth knowing about for final projects. Solenoids, maybe folks have worked with this in the past. This solenoid, it's a very simple actuator. Effectively, you have a magnetized bar inside of a loop of wire, often with a little catch at the end. You send current through the wire to create an opposite magnetic field, and out shoots the bar. You turn it off, and usually there's a spring mechanism to pull it back in. And so you get linear actuation, in, out. It's really handy for like locking doors or latches, stuff like that. You just need in-out motion. I used these, for instance, in a previous project where I needed a device to just drop quarters. And so you have the quarter being held in place by a little solenoid. You click it, click, click, quarter drops, click, click, quarter drops. And so it's these really kind of simple, you just need an in-out motion. These are great. audio speakers move. So depending on the type of actuation that you need, may be the case that you could, if you need back and forth motion over small distances at, kilohertz, hundreds of hertz to kilohertz speeds, you could use an audio speaker as an actuator there. If you need even higher speeds over shorter distances, you could use piezo actuators. Perhaps the craziest project that has ever occurred in this class, it occurred before my time in this class, was a student that I believe used piezo actuators to help him implement a scanning tunneling microscope in 5 weeks with which he could image and move gold atoms. So that requires getting the little end effector really close to the thing that you're trying to image, such that tunneling starts happening, right? So that implies that you need to be able to move things over very small distances very, very precisely. I believe, Bruce, that he used piezos to do that probably, right? Yeah. Unbelievable. That project's linked up on the webpage someplace. You could go find it and take a look. Bruce? Oh, yeah. Have folks heard of nitinol? Nickel titanium? It's a really interesting material. So it looks like wire. You can put current through it like wire, but it has this property that when you heat it up, it shrinks in length by like 2%. Doesn't sound that impressive, but as it shrinks in length by 2%, it does so with a lot of determination. I mean, you can generate kilograms of force from a single nitinol wire by heating it and having it shrink just a little bit, right? And you can lift up kilograms. These are used, we ended up using this material a lot when I was in grad school for some space applications, and they're actually, to my knowledge, used a lot in rovers for things like rover wheels. I think that's true. Another one of their really interesting properties is they are an example of a shape memory alloy. What it means to be a shape memory alloy is you can take this nitinol, looks like a wire, bend it into some shape, and heat it up. And when you heat it up, you have programmed that shape into the nitinol. You allow for it to cool. You can crumple it into any old shape that you want. And when you heat it up again, it goes boing and pops right back into the previously programmed shape. So it is a programmable material. That'll make your brain hurt a little bit. And how do you heat it up? Well, you have a few mechanisms. One way that you can heat it up is just with a heat gun, heat it up, or a heat source of some kind. Or alternatively, you punch a bunch of current through it. And so you can put a whole bunch of current through this as you would a wire. That they're resistive. And so the resistive heating of the nitinol will heat it up, and you can pop it back into some previous shape that it had. One of just the fascinating applications of this that we've been thinking about lately, or at least my previous colleagues over in aerospace have been thinking about lately, is wouldn't it be neat to have a spacecraft that's kind of like a chipsat, like I talked about a little bit, but that's perhaps bigger and bendier, and that has embedded within it these shape memory alloys, so that you could deploy this thing in space, and when it's in space, it's a spacecraft, and then as it starts to be heated by the atmosphere, the heating from the atmosphere would change the shape of the shape memory alloy into an aircraft. And so that you automatically transition from spacecraft to aircraft by way of nitinol being aerothermally heated by hitting the atmosphere. It'd be so cool. Questions about this? Okay. Any mechanisms of actuation I've forgotten? Servos, of course. Yeah. Servo, by the way, when you tear it apart, a servo on the inside ends up just looking essentially like a DC motor with a feedback loop in it. There's a picture of a servo here. So it's a DC motor. There's a potentiometer here being used to figure out what is the current orientation of the DC motor, right? And then that goes through a feedback loop here where we're detecting the error between our desired servo angle and our present servo angle to adjust the voltage to the DC motor to move it to the correct orientation. A lot of the servos that you buy are position control. They're easy to hack into velocity control. What you do is you go in, take it apart, move the potentiometer such that it's in the orientation associated with the middle of the range of the servo. Then you cut the servo line and put it back together. And now when you command the servo to a certain position, it will spin and spin and spin and spin forever. The potentiometer never turns because we've decoupled it from the motor. So it always sees the same error. And so you've turned the position servo into a velocity servo. I have a friend in mechanical engineering who runs the instructional labs. God bless him, who for many years would do this to the servos for the mechatronics course over there on behalf of the students. It's a lot of work. Can anybody guess the #1 failure mode for servos in undergraduate classes? Look at that gear train. There is something, and I don't know what it is, but there's something very tempting about getting a servo and you just want to go and it just blows out the gear train. And so we'll hand out servos, and it's just kind of fun to turn the top, and when you turn the top, you end up blowing out the gears. Okay. So we've talked through DC motors, which require electrical isolation of the sort that we've discussed for Lab 3. We added a conversation about stepper motors. Just remind you that the application space where those make sense for many of your final projects are those where you need low speed, high torque. 3D printers, moving valves. You could come up with a whole bunch of these examples. We talked through about some other more exotic mechanisms for actuation. Depending what you're doing, an audio speaker can be used as an actuator. Small distances, hundreds of hertz to kilohertz speeds. If you want shorter distance control at possibly even greater speed, you're in the realm of piezos, right? And then, of course, you can take a DC motor, pair it with a potentiometer and a feedback control circuit here, and turn it into a servo motor for position control, which is not so difficult to hack into velocity control. And then even more exotic than that, depending on what you're trying to do, there are these shape memory alloys, nickel, titanium, and so forth, that allow for you to pull on things really hard. And of course, linear actuators like solenoids and so forth. Okay. Any questions? Bruce? Right. So Bruce is making the observation that so long as you do not exceed the torque limitation on your stepper motor, then you can count the steps that you have taken, and you know where you are without having a rotary encoder or some kind of motor encoder or a potentiometer or some mechanism of measuring where you are. Do this with great caution, because if you miss a step, well, then you're off, and without any mechanism for feedback, you don't have any way of knowing that you're off, right? So you just stay off. So for purposes of this class and for many of your projects, you can probably get away with that. In an actual industrial application, you would probably be insane to not have some mechanism of feedback associated even with your stepper motors. But if you are not exceeding the torque limitation of the stepper motor, then every time you step, it will click by exactly the amount of degrees associated with a step. How would you exceed the torque limitation on a motor? Well, certainly, hook it up to something that's hard to move, that takes too much torque, and that's going to exceed it. There's a sneakier way to exceed the torque limitation. Torque is just what? Moment of inertia times angular acceleration. And so what that implies is even with a low moment of inertia, something that's pretty easy to move, if your angular acceleration is really high, your torque is really high. So what that implies is if you try to speed the stepper motor up too quickly, that too can exceed the torque capacity of the stepper motor and you will miss steps. And so you have to be cautious that you are ramping its speed up and ramping its speed down so as to not exceed the torque limitation of the motor. So it's not just a function of the thing that you're trying to move, it's also a function of how rapidly you're trying to accelerate it. Any other thoughts about this? Okay, so that being the case, the next topic that I'd like to start to discuss, and it's just going to be a start that'll continue until Monday, is Wi-Fi communication, particularly by way of UDP to start. I will just mention, I mentioned this previously, that if you are communicating over Wi-Fi, you have a couple of options, particularly with the devices that we're using, these Pico Ws. You connect to a network, and you might share data by way of that network, either by way of UDP or TCP. Each has their own sort of sets of advantages and disadvantages. UDP, the one that I want to start by describing, is simpler than TCP. It has less overhead associated with it. In a single packet, there's less meta information about the packet. You just kind of dump the packet out. What that costs you is with UDP, unlike with TCP, you receive no acknowledgement from the device to which you sent that packet. TCP, I send a packet, and I'm going to get an acknowledgement back that the packet was received. And furthermore, I have a guarantee at the sender, as the sender, that the packets that I send will be received in the order that I sent them. There is no such guarantee for UDP. UDP, we just shove packets out the door with a destination address. We receive no acknowledgement that those packets have been received. We have no guarantee that those packets are received in order. But we can send those packets pretty darn fast because there's less of this overhead. There's less handshaking and so forth. And so you find TCP used a lot in things like streaming audio to your computer, for instance. If you occasionally mess up a packet, who cares, right? Are you going to notice it? Maybe. And even if you do, it's going to be momentary. So streaming audio, streaming video, that kind of thing. It's used also in some other things that we'll talk about. Network time protocol occurs over UDP. But in order to start this whole conversation, it seems to me that the place that we should begin is with actually connecting to a network using a Pico W. And so that's the place I'd like to start. Having that conversation, I think this conversation is clearest if we start with just a brief summary of, in general, what happens when you connect a device to a Wi-Fi network. Then we'll talk about what this process looks like in particular for our specific devices and how we use our particular software architecture and SDK in order to facilitate this. But in general, you go home, right? You go to Spectrum or whatever, you get your modem and your router and you plug everything in. What happens? Well, the first thing that's going to happen is your router connects to the broader internet by way of its modem, and from your internet service provider, it will be assigned a public IP address. That is the IP address, the name of that router to the world, right, to the whole internet. After having done that, and when we set this up, you may or may not be prompted for some configurations, or this might also occur automatically, depending on the type of device that you have. It may prompt you for a country code. It just asks you, where are you right now? That allows for it to know what channels and what power levels it is legally allowed to use. It may also just be programmed with a default, or it may know by some other mechanism. And you may or may not be prompted to select a security protocol. The one that we'll be using, as we'll talk about in this class, is WPA2 mixed, which is just kind of the maximizes compatibility with the most number of devices. Having connected to the broader internet, talk to your ISP, and received a public IP address, the next thing your router will do is set up a local network and give itself a private IP address on that local network. These local networks, they are often 192.net IP addresses. If you go home and run ifconfig on your computer and check out your local IP address, it's probably going to look something like this. And it's very often the case that the router will assign itself the IP address 1 on this local network. And furthermore, it often makes itself the gateway for that network. being the gateway for the network means that the device is communicating on that local network. If I'm a device on the local network and I want to talk to another device on the local network, I will send out a packet with that device's IP address. The network will know that that IP address is a local one. It actually knows that by way of a subnet mask. The subnet mask describes, it's a mask, right, that we apply to the IP address. And it specifies which part of this IP address is specifying the network and which part of this IP address is specifying the name of the device on that network. So for instance, with a mask of 255.255.255.0, what that specifies is that the first 3 sections of the IP address will be used to specify the local network name, and the last section will be used to specify the specific device on that network. So if I'm on a local network and you're on a local network and I specify your IP address, by way of this subnet mask, everybody on that network knows, oh, this is another local guy, and they don't go bother the gateway, they just route it straight to the destination address. Alternatively, if I'm on a local network and I specify an IP address that by way of that subnet mask we know is not on the local network, what will happen is the device which has been specified as the gateway for the network receives that packet. On your network, that gateway is your router. And so what that means is if your phone tries to communicate with an IP address that is not there in your house connected to the same network, that packet goes to your router. That router routes it out to the broader internet, right, where it will ultimately be received by the device with which you're trying to communicate. When we connect the device to our local network, the router starts up a DHCP server. This is the system that assigns local IP addresses to devices as they join. So when we join, we're going to connect to our Wi-Fi by way of its name. This is whatever you've called it, right? You get to specify this. And its password that you also specified. When we connect, we talk to the router, and what the router will give to us, it gives us some information. That router will give us a DHCP assigned local IP address. It says, here's your local name, here's your IP address. It furthermore gives us the name of the gateway, so that if I'm trying to communicate to somebody who, by way of the subnet mask, I know is not on my network, I know who to talk to. And it gives us the subnet mask, which we use to figure out who's on the network and who's not on the network. Okay, so this is the whole process that occurs. The part that we are going to talk about related to the Pico specifically really is this section. How do we actually tell the Pico, our microcontroller, I would like for you to please connect to this network, and then I'd like for you to shuffle information around on that network. What if you're on a local network and you want to talk to somebody else on another local network? Anybody know how that happens? But you don't necessarily know their local IP address. It's a different network, right? So it's not relevant to you. The way that this would occur is you would talk to that device on that other network by sending a message to the public IP address of its router to a specific port, and then that router would be configured with port forwarding, so it knows any information I receive through this port, I have been set up to send that to the following local IP address. So it requires some additional configuration. You can imagine that there are some common ones for like SSH, stuff like that, right? Okay. We're about out of time. So what I want to talk about next time is, this is the process in general. What we're going to talk about next time is how, with the Pico W, we do this with our particular device. What is the series of device-specific configurations and commands that we have to implement in order to actually facilitate that more general process. But we'll talk about that next time. I'll be in lab this afternoon. I'll see many of you then. I'll see the rest of you on Monday.